It's a great pleasure this morning to introduce our next plenary speaker, who is Professor Ursula Röthlisberger from the Department of Chemistry here at the EPFL. Ursula has always been a strong friend and supporter of CECAM, and we're looking forward to her lecture this morning, which is entitled Next Generation First Principles-Based Molecular Dynamics from Biological Systems to Materials. Ursula.
Thank you very much for the introduction. It's really an honor and a pleasure to be here to celebrate CECAM's 50th birthday. I think there is no other institution that had so much crucial impact on all the evolution of molecular simulation and also on the community. And here at EPFL, of course, we are kind of celebrating even a double birthday. So the same year as CECAM, there was also the birthday of 50 years of EPFL. So EPFL was founded in the same year. So this is really celebration year for us. So today I would like to talk to you about some of our work that really kind of concern some of the central core issues of molecular simulations. I probably have occupied a big part of the community during all these 50 years, and that is how to kind of push forward the boundaries of molecular simulation, so go to bigger systems, go to longer timescales, go to higher accuracy. And of course, the work in my group has been mainly centered around one special flavor, and that is electronic structure-based molecular dynamics, so first principles molecular dynamics, where some of these restrictions, of course, are even more severe. So all of us, we know that we live in this kind of compromise of having to deal with three different challenges at the time. So in electronic structure, MD, okay, we try to push a bit on the accuracy axis, but you got it much more limited in system size and in sampling time. And of course, the dream would really be that we could kind of perform first principle-based molecular dynamics, but at the cost and the time scales of almost classical force field-based dynamics. So there is this kind of constant dream of somehow somehow reaching this simulation heaven where you can just have it all. So is it possible to really face this kind of combined challenge and not being restricted to just one of the axes? And of course, this is not really only a problem of first principles molecular dynamics. As you know, this is since the beginning of times, this is the perpetual problem in molecular dynamics, and there have been many CECAM workshops that were dedicated to kind of advancing along one of these axes or on several. So from the very beginning, I think when it was possible to do computer simulations already, these were the main themes. So I just had put up here some of these early workshops, and actually some of the participants of the conference, like Giovanni or Jean-Paul Reichert, I think they have been also to all of these very pioneering CECAM workshops already in 1972. There was a 2-month workshop, so this changed quite a bit on MD and MC of water, and then 2 years later already there was the first workshop on advancing timescales. So and then 76, okay, there was already the first workshop on doing protein dynamics. So as I said, accuracy has been an issue from the very beginning. So as soon as people have tried to develop force fields, here is one of the first attempts to do a force field for proteins in 68 by Warshall. So accuracy was the theme from the beginning. And then, of course, increasing system size and complexity from argon to water to proteins. And, of course, timescale, as usual, is always an issue. So at least I can say that at the moment with first principles molecular dynamics, we're just about where classical dynamics started, or a little bit further, so there is at least some hope that we can advance this quite significantly. So in my own group, okay, we have been working on this like many other groups during the years, and I will try to show you some of the things that we have been doing to try to push this boundary forward. Also, some of the most recent work we have done on this. So, of course, our kind of approach to at least increase the size and complexity of the systems that we can treat with first principle based simulation was the QMMM approach, to use a multiscale approach that was also introduced again in the 70s, 76 by Worschel and Levitt. So with the simple idea that you say, okay, let's try to kind of partition our system into an electronically active portion where I really need to make an effort and treat it at electronic structure level, and then taking all the kind of rest of the system into account at a much more expedient computational level, at the level of classical force fields. And okay, in my group already more than 15 years ago, we have been implementing this type of QMMM approach within the context of extended Lagrangian type Garparinella molecular dynamics, actually with the current CECAM Council president has been working on this together also with Joost van der Wondele. And okay, this enables you to do let me go back again. Oops, I'm going forward. So to do, say, ground state simulations of processes that are electronically important, so also forming and breaking of chemical bonds, for example, or systems that are difficult to treat at force field level, like transition metals. And okay, we had also our own approach for taking care of dispersion. That's sometimes a problem within local density functional theory. And as I mentioned, this already enables you to do many things, and QMMM approaches have been developed by many different groups. And here are just a few examples of applications in my group that show you that, okay, you can really go to very large systems, like here nucleosome core particles. So these are the units of packed DNA, where you have a protein core here, and the DNA is wrapped around this to make it as compact as possible in the small space of the cell. And these are systems including water counterions that are around 350,000 atoms. And okay, we have been treating electronically active part here is a transition metal drug that can bind either to the protein part or to the DNA part. And we have been looking at this to try to explain what makes the drug selective for protein or for the DNA part, for example. So you can also extend this and go from the electronic ground state to electronically excited state, and even to non-adiabatic dynamics within time-dependent density functional theory, both in kind of a mean field Ehrenfest type of framework or in Tully surface hopping, or you can even do real-time propagation, TDDFT, and look at the kind of real electron dynamics, like here. You see the kind of electronic rearrangement upon a sudden ionization of a iodo acetylene. So you can all kind of combine this with QMMM simulation and also do this type of excited state application. So you can, for example, look at the optical properties of biological systems and calculate, for example, absorption and emission spectra, or you can do really photo reactions here, so exciting the system and see what kind of chemistry is happening on the excited state surface. Or, as I mentioned, if you do electron dynamics, you can also look at strong field ionization or here radiation damage. So you have already quite many possibilities of kind of systems and problems that you can address. Now, as I mentioned, okay, this was quite a long time ago, and we thought that, okay, it's about time that this type of QMMM interface that we implemented in CPMD, in the Garparinello code, goes to a new generation and, you know, kind of makes some progress, further progress. And actually there is now a new multiscale interface in CPMD that we have been recently been implementing. And this new interface now is not kind of restricted just to QMMM, but to kind of general, very flexible multiscale simulations. So the kind of logic behind this is that, okay, in principle, you have like two different ways of maybe implementing multiscale or QMMM type of methods. You can either have what we call a tightly coupled QMMM scheme. So you try to kind of implement everything in kind of a single package. So that, of course, allows you fast communication, fast data exchange, and you can maybe also optimize it very efficiently because you have this single code that you have to port and optimize for different architectures. But of course, and this is what we actually had at the time with the early interface, the QMM interface in CPMD, but you have very limited flexibility. You're kind of stuck to a single code and maybe do few force fields. We had Chromos and Amber force fields at the time. And so you cannot really arbitrarily increase your accuracy or go to, for example, polarizable force fields, or you don't profit from like automatic upgrades if classical code has become much more efficient. So you kind of stuck with the implementation that you have. And we also hadn't really done extensive parallelization for the MM part at the time. So you can also kind of choose a completely different way and say, okay, I want to do like the kind of minimal implementation effort. Let's kind of just do a loose coupling between, say, QM and MM codes. I leave more or less the codes as they are, and I just let them exchange data, maybe even with scripting. So this, of course, gives you lots of flexibility. You can combine different electronic structure codes with different classical codes. But of course, communication can be very slow. So in principle, it's very nice because it opens you really kind of high flexibility and choice of both the QM and the MM part. But okay, you would like to be as efficient as, say, maybe a tightly coupled scheme. So we have been trying to combine the goods of both sides and have a kind of loosely coupled but highly efficient kind of multiscale implementation, and that is what is called here MIMIC. So MIMIC still has CPMD as the main driver, but it's really made in a way that with kind of minimal effort and minimal invasiveness, you can also couple it to other QM or MM packages, and while maintaining really kind of fast communication with a communication library. So in this way, we can also kind of profit from the work that the classical community does when they come out with new GROMACS or AMBER releases. And also you can do different type of multi-scale simulation. You can chop up the system in more layers. This is already from the initial design. We were kind of planning this. Or you can also do something that looks a bit weird at the first look. You can even use two different methods for the same part of the system. Do, for example, low-level and high-level method for one part of the system. I'm going to come back to that a bit later on. Now, this is quite a large effort, and this is actually a whole team, the MIMIC team, that has been working on that. So the main programmer of MIMIC is Magnus Olsen, who was a postdoc in my group at the time when we started, and now is at University of Tromsø. And also Simone Meloni, who is now just started his faculty position at the University of Ferrara, had a really important role in the design and in the kind of realization of this type of flexible scheme. And also Slava here, a very smart PhD student, had done really a big effort in programming a very good communication library. And then there are many more people, so from my group, that have been working on different extensions. Elisa Liberatore, Nick Browning, Pablo Baudin, and Martin Bircher were all been involved in this and are still involved in this. It's kind of ongoing effort. So, okay, at the moment, the kind of interface is coupling CPMD with Chromax, and Chromax already gives you access to many different force fields, so no longer conversions and so on. You can use your favorite force field also for equilibration and then for QMMM. The whole communication between these two, so these basically are two programs that can run simultaneously and independently, but exchange data efficiently, and that is all handled by the MIMIC interface, and the communication library takes care of reformatting output inputs in a way that the two understand each other, and is doing this directly via intercommunicators in MPI. So it's very, very fast. There is also quite an effort that went into a better parallelization of the QMMM interaction. The expensive part in QMMM in this type of plane wave codes is usually to calculate the interaction of the electronic density at every point of a real space grid with all the classical charges, and that can easily be expensive. So already in the early days we had already two shell scheme where we had close interaction taken into account in this explicit way, and long-range interaction via multipole expansion, and now also the parallelization here has been pushed forward quite a bit, so using both distributed and shared memory parallelization and both different layers of distributing things into task groups, both in terms of planes of the real space grid and in terms of atoms that are coupled. So, okay, this all led to quite a change in the performance. So even so, our old QMMM scheme that you see here in green was what I called a tightly coupled QMMM implementation. So principle has the advantage to be very efficient and have very fast communication. So the new MIMIC interface here is quite a bit faster, so usually almost an order of magnitude faster, and also scales much better. So if you do normal kind of GGA-based DFD, calculations, it scales to several thousands of cores. Here the old one that kind of leveled off very early. Here is the new one that is scaling very well. And if you even go to expensive hybrid functionals within plane waves, then okay, you have scalings behavior that even is going up to 10,000 of cores. So this interface, okay, is now really updated and has kind of a new efficiency. But as I mentioned, okay, this is like the current first implementation, couples Chromax with CPMD, but the whole idea and whole design is that we can couple also different, even electronic structure packages. We're no longer kind of just limited, say, to use DFD within CPMD, but couple it to the favorite quantum method that you want, or the favorite classical code that you want. And at the same time, CPMD remains the main driver, but you can obtain forces from different other packages. And within this, okay, we can also profit from many of the things that are in CPMD, like force matching, enhanced sampling techniques, and so on. So having this flexibility and having also possibility now to even go to higher accuracy, and you can say, okay, you have first principles, you do already the UFT calculation, why do you bother of kind of pushing the accuracy? But the accuracy can still be a problem, especially if you go to excited state dynamics and to non-adiabatic dynamics. TDDFT can have some problems. Maybe you want to have better better functionals or even multi-reference methods sometimes. So we would really like to have this flexibility of kind of also going up even further on the accuracy level. Now, of course, having the possibility is one thing, but you also have to be able to afford it. So we have to find a way that these even higher level methods become efficient enough that we can run reasonable molecular dynamics simulations. And we have been working on this quite a bit, and we actually have been exploiting in many different ways something that was developed in the early 90s by also one of the participants in the conference, Mark Tuckerman, together with Bruce Byrne and Glenn Martina, who introduced multiple time step propagations. And actually we use this really to kind of speed up this type of different high level, low level type of combination. So I'm going to explain this a little bit in more detail. So let's assume you do QMMM or even a full first principle simulation at a density functional level, and okay, in plane waves, for reasons of efficiency, for a long time we were kind of restricted mostly to generalized gradient approximation. So already to go, say, one step further, to go to hybrid usually costs you quite a bit, even though people have made efforts to do really efficient polarization with the IBM team, so already became better. And also in my group, we have been working on that, so trying slowly to climb here the Jacob's ladder towards at least the rung 4 type of functionals. So Martin Bircher, in my group, he has been implementing a kind of new flexible general exchange correlation driver in CPMD that allows you also to kind of customize your own functionals, but he also implemented range separated hybrid functionals like CAM Beasley LYP or the Trular Minnesota family. And at the same time, we had also found a trick that we can speed up this type of hybrids or exact exchange functional calculation within plane waves by using simple scaling relations for the exact exchange. And this works if you have like an isolated system with a big box. So then actually you can start playing with different resolution of the mesh to calculate your exact exchange, and that leads to speed ups of almost 1 order of magnitude, so roughly 8 times faster, so that we can afford better this type of hybrid calculations. But even further, as I mentioned, and okay, if you want to know more about that, Martin has a poster, and you can have a look about all the kind of details about this. Okay, so I mentioned also we really try to exploit this type of multiple time scale propagations, and the whole idea behind that is, okay, if you want to increase the accuracy of your electronic structure method in quantum chemistry, going to higher level is always fighting to have more correlation. So we go to the full CI, it's exact solution. So all the efforts you do is to get better description of the electron correlation. And if you look at the kind of contribution to the total energy, this contribution is usually very small. So, and also if you, for example, think of density functional theory, so exchange correlation part, if you look at the forces on the nuclei that come from this, then, okay, the exchange correlation part doesn't have a direct dependence on the nuclear position, only an indirect one. So actually looking at this, you could think like, okay, is this contribution to the force so big? And maybe also, is it really slowly varying in time? So if I compare, for example, MD simulation, I calculate my forces at the GGA level, or I calculate them at the hybrid level, and okay, I calculate this difference between the force contribution at the low and the high level, this delta Fi here. So kind of hope is that this is something actually rather small and especially varying kind of slowly in time. And if you look at this, and I've been looking at this for different systems, Elisa Liberatore, my group, had been starting this work. So here we have a liquid water box. And okay, here you see kind of forces on one of the components of the forces on one of the atoms. They look all about the same. And what you can see here actually in blue is the force that we calculate at the LDA level. And what you can see in red is the corresponding force for the same configuration at the hybrid PBE0 level. And if you take the difference between the two, you get this line here, which obviously has kind of some oscillations, but varies much smaller, much more less rapidly in time, and is also rather small. And you can do this kind of game with different type of electronic structure methods. So you can compare PBE with MP2. So here again, blue PBE forces for a water dimer, here in red MP2 forces, here in purple the difference that is really kind of slowly varying. So all the effort we do is, say, if we run a low-level MD calculation, all the effort is to have this kind of additional correction to the force, this delta F here. So as this is kind of varying slowly in time, as I said, we could profit from multiple time-step integration and actually integrate slow parts of the forces with a longer time step than fast components. And as I mentioned in the early 90s, Mark and collaborators have been implementing this and developing these reversible multiple time step integrators that allow you just to do this. So if you can split up your force into a slow component and into a fast component, then okay, you can propagate the entire system by propagating the fast part with a small time step, delta t, and the slow component of the force with a much larger time step. And okay, in our case now, the fast force is the kind of low level that we can afford, that is already good estimation of the true force that we can calculate fairly quickly. And okay, the slow part of the force is the correction that we get from a higher level method. But again, using this, and as this slow part can be integrated with a much larger time step, we have to evaluate the high level at much less frequent intervals. So of course the physical propagation of the system is in the big time steps, but you have an inner loop where you propagate the system with small time step with part of the force that you get at the low level. But the resulting dynamics is the dynamics at the high level, but for a much reduced cost. Okay, so we have been doing different combinations of making use of this with, as I mentioned first, kind of combining LDA with PB0, PBE with PB0. For example, here we're doing this type of multiple time step simulations for liquid water. So everybody knows LDA water is terrible. It's not quite water, it's essentially ice. So there's a big difference now between what we actually do at the low level, it's LDA, and what we should get here in red, which is the PB0 curve. And okay, doing this multiple time step integration using LDA as first guess, but doing the corrections every a large time step, we kind of recover completely the high level radial correlation function here. Now, the kind of ratios that we can have between, say, the small time step and the large time step, of course, depend on the system, how well you can really separate the slow from the high frequency parts. So typically you can do maybe a ratio of 5. If we kind of use And this is limited by some resonances still, that the force components are not completely separated. So if you use a stochastic thermostat, here we were using a colored noise thermostat developed by Gioriotti Bussi and Michele. So then you can even push it further. So here we have been running a larger time step of 3.6 femtoseconds with the inner time step of about half of a femtosecond. And you can do this for different systems. Again, the low level can be rather different. Here we had a water cluster that actually in a certain conformer is not even stable at the GGA level, so just dissociates. And okay, if you still use this as a first guess, you do the correction at the high level, you recover the dynamics at the B3 LYP level. And okay, you have significant speed ups for this because you have to evaluate the high level only ever so many times. Now you can do the same thing for excited state dynamics. You can do it for adiabatic excited state dynamics. This has been developed by a postdoc in my group, Pablo Baudin. And here again, we are combining now TDDFD at different levels, say at LDA and PB0 level. Even you can also have different basis sets if you like, or you can also extend it to non-adiabatic dynamics. You have to be a bit more careful in non-adiabatic dynamics because, okay, if you do very large time steps and you, for example, evaluate your non-adiabatic coupling every large time step, you may miss actually a kind of region of high non-adiabatic coupling in between. So we actually use some indicators, like Landau-Sehner type indicators, to tell us when we propagate in the small time step, when do we get to a non-adiabatic region, and then, okay, we will recalculate the non-adiabatic terms fully. But even for this, the ratios are a bit smaller, but you can still speed up non-adiabatic dynamics by factor 2 to 3, which is quite a bit if you think of computer time. If you run something 1 month or 3 months, is still a big difference. Now, as I mentioned, we are not kind of married to DFT anymore, but we can also now try to go to even higher level, can combine it with wave function based methods, MP2, coupled cluster, and I just show you some examples here for MP2 dynamics. So here the low level is again PBE, high level is MP2. So here low level is PBE with plane wave basis, high level is MP2 with a OXCCPVT set basis set. And again, like here you see the forces, for example, for PBE and MP2, and the difference has some oscillation, but is still much smoother. So in this way, we can also run MP2 dynamics for really a fraction of the price. You could also think of, instead of always going upwards in accuracy, you could think of going downwards, because we should always choose the accuracy that you really need. And maybe for certain problems, we don't even need DFT. Maybe we can go to semi-empirical, or we could even go further down and say, what about force fields? So could we use a classical force field as low-level method to give us a first estimate on the nuclear forces, and then, okay, evaluate every large time step an electronic structure force and use this as a correction? And this is what we have been doing here. So basically running classical MD, but with the accuracy of an electronic structure method. And okay, you can do this. Again, we have been doing this for water here, TIP3P. You can get significant speed ups, again, like maybe factor 6 to even factor 10. Here, the main kind of limitation is that we don't have really a very good flexible water model, so we had to make TIP3P flexible to do that. So the kind of limitation in speed up is because we still have some high frequency components in the correction forces to come due to the fact that the flexible water is not completely vibrating in the way it should at the DFT level. So actually to solve this, what helps a lot is when you do kind of consistent force field that you can develop, for example, by force matching. So by definition, the force field is chosen in a way that the difference in the forces at the force field level or at the QM level are minimized. And like this, you can really use it as a very good guess already and run this at the lower level. But you can also say, okay, if I can do it with force fields, maybe I don't even need a force field. Sometimes it's very cumbersome to have really a good force field. Okay, you can automatize things up to a certain extent, maybe with force matching, but it's always an effort to have a good force field. So question is, okay, do I need a force field, or could I maybe just do it by machine learning? And molecular dynamics, of course, is something that offers itself, say, to machine learning, because we think that we're calculating 10,000, 100,000 configurations each time, energy and forces, energy and forces, energy and forces. And okay, if you do like liquid water, for example, system is sampling similar configuration, you would think that at some point after this 100,000 times that I've done that, there should be a way that I can kind of know what the energy and the forces are for a certain configuration. So certainly you have lots of data available, and that should be a good kind of starting point to use machine learning for that. So okay, we have been trying to do this kind of as an experiment. Okay, how far do we get with this? How good is it? And can we use it in this type of multiple time step propagation? So Nick Browning in my group has been implementing a rather recent approach that Anatol von Lilienfeld introduced, which is called Operated Quantum Machine Learning, OQML, and that allows you actually to calculate, for example, response properties within a machine learning model in a very efficient way. And okay, it's based on a kind of atomic decomposition of the energy that is then expanded in kernel function. And if you want the corresponding forces, okay, you just have to do the derivative of this expression. So he has been implementing this together with representation, the A-slatum atomic spectrum of London Axelrod-Mutter potentials, Axelrod-Teller-Mutter potential, that was also suggested some time ago by Anatol. We have not experimented too much with different representations, just wanted to know, okay, let's take a reasonable one and see what happens. So this specific one is basically made out of single atom terms, pair potential, and three body terms. So with this, okay, we tried again our favorite example, liquid water. That is kind of not so trivial. So, and what we have been doing here is doing a machine learning model to predict the difference between LDA and PB0 forces, or to do a machine learning model directly predicting PB0. So, okay, you can see here the kind of errors with increasing training set size that go nicely down. And what we can reach already for fairly small kind of training sets, we get very good accuracy for the forces of less than like 0.15 kcal per mole per angstrom, also very small angular error. And even for direct learning, okay, we have errors that are less than 2 kcal per mole per angstrom, already a very good start. And you can see here are the forces plotted that you get from LDA here in this greenish color, and here is what you get after the machine learning correction compared to the PB0 reference. Also, this is fast, so you can train this machine learning model in about 3 minutes on a workstation, and every ML prediction is very fast, takes about 1 second, compared to, say, 5 or so at the LDA, or on the workstation, PB0 takes a long time, it's almost an hour. So we have been using now this to test different type of combinations. So can we use machine learning model to have a better low-level estimate, so that it's actually so good that the difference to the high level is so small that these correcting forces are really very small, and we can do very, very long time step ratios? Or, okay, can we directly predict the high-level forces? So here again, this is the example of liquid water, where we use LDA as a starting point, again, pair correlation function here in blue. And okay, our reference is PB0 here. We could also take something else, already with a multiple time step thing. This is the red curve here. And here we have 3 different schemes, actually 2 different schemes to do this combination with machine learning model within an MTS scheme. So for the first one, actually, we used the machine learning model to predict the correction. We do LDA, we let the machine learning model predict the high level. So basically, we don't ever have to evaluate the high level anymore. So very cheap. It's kind of the cost of a GGA with the accuracy, hopefully, of a hybrid level. And this is what we have here in scheme 1. This is the blue curve, and you can see this is kind of perfectly reproducing the high level pair correlation function. In the other one, we were a bit more conservative and said, okay, we do LDA as low level, but okay, we kind of improve it as a guess with the machine learning model, so that it's already very close to hybrid, but we still do the evaluation of the PB0 forces, so this dynamics is really PB0. And this is what you see here in green, okay? See, it's about the same accuracy. Here is when we do it just machine learning without any MTS, at least for this system, even this worked. So, okay, both schemes. Scheme 1, of course, is very fast. It's 50 times faster. You can really run basically GGA level dynamics with the accuracy of a hybrid method. The other scheme is also efficient. It's kind of certainly preserves completely the accuracy of the hybrid level, and we can afford much larger time step ratio, because now the force corrections are really small, so this is at least factor 10 faster. So, okay, with this, I think I have to wrap up here. So we also tried other systems, for example here, materials-oriented systems. We're also using artificial intelligence approaches in other contexts. For example, not only to do MD, but also to analyze high-dimensional simulation data by feature selection, and also use genetic algorithms for inverse design applications, for example, to design biomimetic compounds, and use genetic algorithms to explore the vast space. And here we have one example where we were able to design a very efficient metallovariant, highly thermostable metallovariant of a small biomimetic system, and also express the mutants and characterize them. Whatever analysis of data, but I don't think I have time for this, so I think I should go here and well, thank my group for all the work. So I showed you already with the faces going through, but just to see that I didn't forget anybody that I mentioned before. So Paramveer Alavat here is working on a perovskite system. He has also a poster. Svanendu is also working on excited state dynamics. Ariadne Matthias and perovskites. Polydevkis on DNA, Simone on Guido on biomimetics, Farsane on perovskites, and Marco too. Then Maria Letizia on some biological application. Francois is taking over from Nick on the machine learning part. Murat also bioapplication. Justin is working on the DFT parts, and Thibaut on the big DNA simulations. And of course, there are always the quadrupeds also in the group here that have an important function here for the social life. So I thank you very much, and happy birthday again for CECAM.
Thank you very much, Ursula. We have some time for questions. Please. If you just wait for the microphone.
Maybe I miss some point in your very comprehensive talk, and how do you treat the sometimes very important memory electron correlation effects with time-dependent DFT? I think this is kind of one of the bottlenecks of the theory, memory correlation, right?
Yeah, but I mean, all the kind of simulations that we do are completely in ALDA, so completely local approximation for exchange correlation functional.
So no memory, right?
No memory effect. They are, with the time-dependent real-time propagation, as you solve the time-dependent Konjam equations, even within, these functionals, you may have some memory effects due to the propagation, but there are no explicit memory effects there.
No true electron correlation, right? Kind of. Okay.
Yes, no, within the DFT things, no.
Mm-hmm. Okay.
Other questions? I have there's one over there. Chris.
So very nice talk, and actually it's very interesting, this part of the multi-time scale integration. But I missed maybe the point, how do you combine the forces? Because as I understood, you switch between different levels of theory, or how do you weight the difference between them to avoid the discontinuity from switching from one level of theory and computing the forces to the other one?
There is no real discontinuity. This is really in the multiple time-step propagation. You could do that at the classical level also. For example, if you chop up the classical force in a force field-based MD and say, for example, I have my high-frequency components that come from maybe vibrations or so, and then I have my maybe very slowly varying components of the force that come maybe from van der Waals type interaction. So if I can say, okay, I chop up my force into this fast component plus a slow component, that's the total force, then, okay, I can do the propagation in different time steps. But in the outer time step, you always have the full force. So what you do is a propagation with the full force. So what comes from your force field, in our case, what comes from the high-level method. But we do already inner kind of propagation with a small time step with a lower level method. But there is no kind of a switch, say, from one method to the other, because the kind of Hamiltonian that is underlying your dynamics is the one at the high level.
Okay, thank you.
Sure, I wonder if I could ask you a question. I'm a great proponent of these multiple time step methods, but I wonder if there's a way of using machine learning, for instance, to recognize when the long-range part of the force, the slowly varying part, misbehaves.
Yes.
So that you now need to go back in and do the full calculation,
Absolutely.
not at regular intervals, but whenever something occurs, which means a full calculation is required.
I mean, this is really what, our goal is, that we have a fully adaptive scheme. So that's also one reason why we wanted a machine learning approach where we can retrain fairly quickly on the fly. And the idea is really that you can adapt this ratio of the two time steps. You can say it's 1, and then I evaluate high level at every time step, or I can say it's 40, and or you know, even higher, because I'm already happy with the low level. So if you find a way of predicting when you get into a region where things are not so good anymore, and okay, you can have different measures for that. You can have like kind of maximum deviation, that your force correction goes beyond a certain threshold, or the different measures that you can take. Then you can kind of adapt this ratio on the fly. And basically the idea is that you run, okay, as long as your machine learning model is very good, okay, fine, I can basically run with machine learning. If then I get to configurations that are a bit outside of what I trained, I switch to the ratio 1. I do full first principles MD. I put this into a training set, I retrain, and there you go again. So the idea is really to have it fully on the fly and adaptive.
So we have time for one more question, which is in the front here.
This is a follow-up question to the former question, where you propagate on these two different time scales,
Yes.
The fast time scale,
Yes.
so smaller step with a low level.
Mm-hmm.
How do you actually estimate what the right time step is for the higher level calculation?
Mm-hmm.
How do you get an idea what's the right?
With the usual energy conservation, you know, we run NVE and we monitor the energy conservation. And okay, you saw the plots that I showed you as a function of ratio also, how the energy conservation deteriorates. So we say I'm willing to accept 1 part in 100,000 or so, which I consider as a good energy conservation, and that determines your time. So a bit like always, you know, in any kind of MD, you have to decide your time step, and okay, if it's too big, then your integration is...
So there's an energy conservation for
yes.
the long time step, and there's an energy conservation
There's
for the
only an energy conservation for the long time step. That's the real physical propagation. The other one is not a physical propagation, it's propagation with a component of the force. So the real dynamics is only at the outer level. It's like the example for classical, if I propagate and I integrate my vibrations, I mean, the true dynamics is only when I have the full force, taking everything into account, so only at the big time steps.
So then how do you choose the small time step?
The small time step, again, we choose the ratio between the large and the big ones via energy conservation. Again, if you make it too big, then the energy conservation deteriorates. I mean, you've seen
So
the
it's
plots. I mean, it's the usual Verlet.
The one
behavior.
energy conservation.
Yes.
Okay,
Yes.
thank you.
I would like to thank Ursula for a talk. But before you disappear for coffee, Ignacio has a number of announcements. So should we just say thank you?
A few announcements. Today there are 2. First is that on Monday I told you that we would have the photo now, but due to a problem with the organization, we will have the photo of the conference in the coffee break of the afternoon. The afternoon will be a tight schedule, so we will remind this to you, but please keep in mind that when we finish the first part of the afternoon, it's very important that we try to go as fast as possible upstairs. Outside the building, we will have in the esplanade the photo, so that we have time for the coffee break before starting the second half of the afternoon. The second announcement is that tonight we will have the conference at the Olympia Museum, and from 6:30 the museum closes to the public, and then the whole building is only for us. I remind you that we have free access to the museum if you want to visit, and then we will have an aperitif. I think the day is nice. It will be in the gardens, starting at 7:15 until 8:15. Now, in order to do that and to benefit from it, it is very important that you take the badge with you. You are scanned when you come here in the morning. You will be scanned in the Olympic Museum. If you forget it, then you will be in trouble. Okay, so please remember, and then you have free access to the whole building for the rest of the night. Okay, thank you. Now we can go to the coffee break.